Hi, my name's Dr. Terry Brown, and in this engineering mechanics video lecture we're going to look at friction and wedges. Now in this application of wedges, typically what we use wedges for is to adjust the elevation or to provide stability for heavy objects. In this case we've got a large steel pressure vessel, and we've used the wedge down here to keep it in place. So we might want to know what force is required to pull the wedge out, because we've got this large weight acting down on top of it. Or we might want to know, if we have no force applied here, whether this system will be self-locking. Right? Will this wedge get pushed out by the weight of the pressure vessel acting on it, or will it lock the pressure vessel in place? And what physical conditions do we need for this locking to take place, or conversely, will the wedge come out? Another application is to provide a gripping force or a clamping force. So we can use wedges to provide a grip or a clamping force on this specimen, for example, that is in a testing machine. So we're applying our force down here to the specimen, and we want to make sure that under no matter what magnitude of force we apply here, that the grips will stop the specimen from moving. Okay, so let's look at how we analyze the wedge. So first of all, we just can think of a wedge as a simple machine in which a small or relatively small force P can be used to push a large or to lift a large weight W. Okay, so we push in here and we want to lift this weight W, and for this simple machine the force that we apply here at P is less than the weight that we want to lift W. To determine the force required to push the wedge in or out, as the case with most engineering, if not all engineering mechanics problems, we need to draw some free body diagrams. Okay, so we've drawn here the free body diagram of the wedge, and it's usually easier to start with a free body diagram of the wedge, because usually we'll know the direction of its impending motion. Okay, so here we're pushing the wedge in, so we know that the impending motion is to the right. So we know from that if we're wanting to move this wedge to the right and we've got friction here opposing that motion, then we can put our friction forces in and we can indicate the sense or direction of those friction forces. Okay, so when we draw the free body diagram, so we note that the friction force always opposes the impending motion, so we always draw our friction forces in a direction opposite to the motion or impending motion. The friction forces are always parallel or tangent to the contacting surfaces, and the normal forces are perpendicular to the contacting surfaces. Okay, so now we'll look at the block. So we draw the free body diagram of the block, and note that at the contacting surfaces between the wedge and the object, the forces are equal in magnitude and opposite in direction to those on the wedge. So if we just look back at the free body diagram of the wedge, we can see this surface here is this surface here on the wedge is in contact with this surface here of the block that's sitting on top of it. So where we had our force from friction opposing the impending motion of the block, acting to the left here for F2, on the contacting surface on the block sitting on top of it, that force F2 will be equal and opposite to the one that's on the wedge. And similarly for our normal reaction force. So we've got the weight of the block coming through here as a normal force acting on the wedge. So we have equal and opposite normal reaction force acting on the bottom of the block that sits on top. And the as we push the wedge in, we're moving this block upwards. So on the right hand side here on this contacting surface with the wall, we have our friction force acting downwards. This friction force is pushing the block into the wall, so we have a normal reaction force here on this vertical wall of the block. We should also show all other forces acting on the object, right, as we've just discussed here with regards to this weight force and the contacting forces between the block and the wall. To determine all of the unknowns, we can now apply our equations of equilibrium. Some of the forces in the x direction equal 0, some of the forces in the y direction equal 0, and if we're wanting to work out what's the force we need to make the wedge move, then we must be reaching the limiting condition where every surface is on the point of sliding. So in this case we can apply our friction equation, F equals coefficient of friction times the normal reaction force, right, because we have impending motion. Okay, so when we start to do a problem where we're analysing a wedge with a block sitting on top of it, which of the two free body diagrams should we start analysing first? Right. The answer is we should start analysing the free body diagram in which the number of unknowns are less than or equal to the number of equations, because otherwise we can't solve anything. Okay, so the number of unknowns must be equal to or less than the number of equations. So if we move on now to looking at the case where we want to remove a wedge from a block sitting on top of it. So now we've reversed the direction of the force, so we want to know what force we need to pull this wedge out. Our impending motion is now to the left. Okay, so if we do the analysis here and we work out the force P required to remove the wedge, if that force P is positive, so we have to apply a force to get it to move out, then we know that the wedge is self-locking, and if we had no force there, it will not just move out on its own. Okay, so if it will move out on its own, then the value of P that we calculate will come out to be negative. The conditions where the wedge might come out on its own are fairly obviously if the coefficient of friction is too small, and I guess less obviously if the wedge angle theta is too large. Okay, so let's have a look at an example. So in this example problem, we've got a load here that weighs 100 newtons, and we have a coefficient of friction between surfaces AC. So down here we've got surface AC and surface here BD. The coefficient of friction between those surfaces is 0.3. We have some rollers in here, and they're smooth, so we can assume that there's no friction generated or negligible friction generated between the two surfaces here. And we're also told that we can assume that the wedges and the rollers have negligible weights for making this problem just a little bit simpler. If you needed to take that into account, it's not too difficult to do so. It just makes the problem just a little bit longer. Okay, so in this problem we want to know what force P is required to push on this wedge to be able to lift the load vertically by a small amount. So our plan of attack is to draw a free body diagram of wedge A. So before I talk about that, stop the recording and have a think about why we might do A first. So think about that for yourself. Maybe go back some of the previous slides in the video and think about why that is. Okay, so hopefully you've had a think about that. So the reason that we do free body diagram of wedge A first is because that's where we're applying the load, that's where we know the impending motion, so that makes it easier for us to draw the correct sense or direction of the friction forces. Okay, so then we go and draw a free body diagram of wedge B, and then we apply equations of equilibrium to wedge B. So again, think about why do we apply the equations of equilibrium to the wedge B here first. So again, pause the video, go back and look at some of the previous slides and have a think about why we're applying the equations of equilibrium to wedge B first. Okay, now that you've had a think about that, the reason that we apply the equations of equilibrium to wedge B first is because that's the only part of the system in which we have a known input into the free body diagram. So the only thing that we know in terms of loads is the weight of the block here. Okay, so in order to be able to calculate something straight away, the free body diagram of the block and this wedge will be the only one that we can use in our equations of equilibrium to calculate something straight away. So then once we've done that and we've calculated some friction and normal reaction forces, we can then go and apply the equations of equilibrium to wedge A. Okay, so our free body diagram of wedge A, so we're pushing into from the left here, pushing the wedge A to the right. On this bottom surface here, we're contacting with the ground, and we were told that the coefficient of friction was 0.3, and we're on the point of slipping, so we can apply our equation of friction, our friction equation, F equals mu n equals 0.3 times the normal reaction force. Okay, so again a reminder that we can only apply that if we have the condition of impending motion or at the point of slipping. So returning to our free body diagram of the wedge over here, we've also got the weight of the block down onto the wedge through the rollers and then acting on this top surface of the wedge. No friction force parallel to the surface because we've got rollers, so we've just got our normal reaction force perpendicular to that surface. Okay, so if we now draw a free body diagram of the wedge B, so where we have I guess sort of contact here, we've got the rollers in between, but the normal reaction force that we have on the top of wedge A, we have equal and opposite acting on this bottom edge of wedge B. We have the weight of the block sitting on top acting downwards of 100 newtons, and then over on the right hand side here where we've got contact with the wall, right, this force here P on the wedge is wanting to push it to the right and wanting to push this block B upwards, so our friction force opposes that motion, so it will be acting down and parallel to that surface, and we've got a component of N2 pushing in, so we've got a reaction force N3 from the wall on that block B. Okay, so let's start by applying our equations of equilibrium to wedge B. So looking at this one up here, and if we take some of the forces in the horizontal direction first, so some of the forces in the X or horizontal direction, we have the horizontal component of N2, so that will be this component here, right, so the opposite, so that will be N2 sine 10 degrees minus our normal reaction force at the wall N3. And if we look at some of the forces in the vertical direction equals 0, we have the vertical component, so this is the adjacent component here, so N2 cos 10 degrees acting upwards positive, minus the 100 Newton load, minus our friction force, which we can apply our friction equation directly, so the friction force at surface 3 here will be equal to 0.3 times n subscript 3. Okay, so here we have two equations and two unknowns N2 and N3, so we need to solve those two equations simultaneously. I'll let you do that for yourself, I'm not going to go through that. And if you do that correctly, you should get N2 equals 107.2 newtons and N3 equals 18.6 newtons. Okay, so if we now apply the equations of equilibrium to wedge A, so we now have N2 that we solved from the first free body diagram. So we can put that into our system and then we can solve for our other unknowns. So again, applying some of the forces in the vertical direction equals 0. We have N1 minus N2, which we worked out to be 107.2, and we want this component here, which will be the adjacent side of the right angle triangle, so 1072 cos 10 degrees, and in this case they're the only two forces in the vertical direction, so we have one equation, one unknown, and we can solve for that straight away to get N1 equals 105.6 newtons. And then if we apply the sum of the forces in the x direction equals 0, we have P minus the horizontal component of N2 here. So again, that was 107.2. The horizontal component is this opposite, so N2 sine 10 degrees in the negative direction, and the friction force on this bottom surface here, and again, because we're at the point of slipping, we can apply F equals mu n, so 0.3 times N1. N1 we calculated up here, so that leaves us with our only unknown being our force P, and if we solve that, we get P equals 50.3 newtons. Okay, so that's the end of the problem, and just thinking about this application of wedges and the fact that we use a relatively smaller force to lift a larger weight than that force. We can see here that we're applying a load, a force of 50.3 newtons, and the load that we're trying to lift is 100 newtons. So we get a mechanical advantage here of about 2 to 1. Okay, so just a couple of multiple choice quizzes to finish off at the end here. So as I've just said, you should be able to get this fairly quickly. So just pause the video and think about your answer. So a wedge allows a small force P to lift a relatively large weight W. Okay, so we've got another multiple choice question here. Determine the direction of the friction force on object B at the contact point between A and B. So again, pause the video, have a think about the problem, maybe draw some free body diagrams on a piece of paper, and think about what your answer is before I give it to you. Okay, so the correct answer in this case is C. Okay, so some of you may have had D as the correct answer, or as what you thought was the correct answer, but be careful to look at the question carefully. So what we're asked for is the direction of the friction force on object B. Okay, so that's this one here. So if we do a free body diagram of the wedge, this would be the force, the friction force on the top surface of the wedge. So therefore on object B we need equal and opposite to that, which will be this force here acting in this direction tangent to that top surface of the wedge. Okay, and finally, when we're determining the force P needed to lift the block of weight W, it is easier to draw a free body diagram of which part first. So again, pause the video, stop and have a think about what your answer is, go back and look at what we've discussed previously. So the correct answer for this, of course, is the wedge. Okay, because we know the impending motion direction, so we can draw the correct sense of our friction force. Okay, so that's the end of this video lecture. I hope you found that helpful. And if you're interested in looking at some more example problems, I'll do this as a video tutorial, which you will be able to find on my YouTube channel. Okay, so thanks for that, and I'll see you next time.